At 7:29 in the evening, Universal Time, on the longest day of the year, a piece of the sun the size of several Earths let go. It happened on the solstice, June 21st, a region of the sun that didn't even have a name a week ago, now catalogued as active region 4473, unloaded a flare measured at M7, almost an X, almost the strongest category we have. The radiation arrived here in 8 minutes and 19 seconds. That's how long light takes to cross from the sun to your sky. By the time anyone at NOAA saw the spike on the GOES X-ray monitors, it was already over, already done. The sunlit half of Earth had taken the hit. For a few minutes, shortwave radios on the daylight side of the planet went quiet. Pilots on transoceanic routes lost the high-frequency channels they rely on over open water. Ham operators watched their signals fade into static. NOAA logged it as an R2 radio blackout. Moderate, not catastrophic, not the end of anything. So why am I telling you about it? Because of when it happened. Here's the thing almost no one is saying out loud. The sun is supposed to be calming down right now. The peak of this solar cycle is behind us. We passed it back in October of 2024. We're on the downslope, the quiet side of the mountain. And the quiet side of the mountain is exactly where the most dangerous storms in recorded history have come from. By the end of this video, you're going to understand 3 things. You'll understand what actually happened on the sun this weekend, in plain language, with the real numbers from the agencies that track it. You'll understand why a fading solar cycle is not the same thing as a safe one, and you'll understand why a single region, rotating toward us right now, has space weather forecasters watching their screens a little more closely than they were a week ago. This is the Horizon Lab. We don't do panic here. We do the truth, with the data on the screen, because the truth is usually stranger than the scary version you've been sold. If that's your kind of thing, take 1 second and subscribe. It genuinely helps this channel reach more people. And tell me in the comments where you're watching from. I want to see how far this sky stretches. Let's get into it. Start with the object itself. Active region 4473, a sunspot group. If you could stand off to the side and look at it, you'd see a dark, churning bruise on the surface of the sun, cooler than the blinding photosphere around it, which is the only reason it looks dark at all. It isn't dark, it's just a few thousand degrees less ferocious than its surroundings. What makes a sunspot dangerous isn't its color, it's its magnetism. The forecasters who classify these regions gave 4473 a label that sounds like alphabet soup, beta, gamma, delta. Hold on to that phrase because it matters, and I'll come back to it. For now, just know this. That label is the sun's equivalent of a coiled spring. It means the magnetic field inside that region is twisted, tangled, and storing an enormous amount of energy in a very small space. And twisted magnetic fields do not stay twisted forever. When one snaps, you get a flare. The M7 on the Solstice wasn't even alone. In the same 24-hour stretch, the same region fired off an M3 and an M2.6, smaller siblings. A region this active, this fast, this early in its trip across the face of the sun gets people's attention, because 4473 is only just rotating into view. It has the entire crossing ahead of it, 2 weeks roughly, where it's pointed somewhere near us. And it is not the only thing on the menu. There's something else out there, on the far side of the sun, that I'll show you later. Something that has been growing, fast. But before we get to what's coming, we have to be honest about what's already here. And what's already here is a contradiction that doesn't make sense until you understand how the sun actually works. Let's talk about that R2 label, because NOAA's scales are the key to not freaking out, and also to not underreacting. Space weather comes in 3 flavors, and NOAA scores each one separately. There's R for radio blackouts, the stuff caused by the flare's X-rays. There's S for solar radiation storms, caused by high-energy protons. And there's G for geomagnetic storms, the big, planet-shaking ones caused by clouds of magnetized gas slamming into Earth's magnetic field. R, S, and G. Each one runs from 1 to 5. Each one measures a different piece of the same event. The solstice flare scored an R2, moderate. On a 1 to 5 scale, that's the low end. So what does a 2 actually mean for a human being? It means that for about an hour, on the side of Earth facing the sun, the upper atmosphere got slammed with X-rays and soaked up extra energy. That upper layer, the ionosphere, is the mirror that long-distance radio signals bounce off of. Juice it up with sudden radiation, and it stops being a clean mirror. High-frequency radio, the kind that carries voices across oceans where there are no cell towers and no cables, degrades or drops out completely. Now, who actually uses that kind of radio in 2026? More people than you'd think. Airliners on the long polar and oceanic routes, the ones far from any ground station, lean on high-frequency radio as a backup, and sometimes as a primary link. Mariners out past the horizon, ham operators, search and rescue teams, some military communications. For all of them, an R2 is a bad hour, annoying, occasionally serious, but survivable, and over quickly. Here's the part that matters. That radiation, the flare itself, travels at the speed of light. It left the sun and reached Earth in about 8 minutes. There is no warning for a flare. By the time you detect it, it has already done what it's going to do. You don't forecast a flare's arrival. You forecast whether the region that made it is loaded to make another one. And 4473 is loaded. Now step back and look at the bigger rhythm, because a region this feisty showing up now is a little like hearing thunder on what's supposed to be the clear day after the storm. The sun is not a steady light bulb. It breathes. It runs on a roughly 11-year cycle, swinging from quiet to violent and back to quiet again. At the bottom of the cycle, the surface can go days, even weeks, with barely a spot on it. At the top, the so-called solar maximum, the face of the sun, is a mess of churning regions, flares going off like a stadium full of camera flashes. We have been near the top. Cycle 25, the cycle we're living through right now, hit its peak in the fall of 2024. The fall of 2024, that's more than a year and a half ago now, which means, on paper, the sun should be settling, winding down, heading for the quiet years. So why did it just throw an almost X-class flare on the solstice? Why is a brand new region this angry this fast? And why, if the worst is supposedly behind us, are the people whose job it is to watch the sun not relaxing? The answer is the single most misunderstood thing about space weather. And once you get it, you'll never hear the phrase, "the sun is calming down" the same way again. So let's actually explain the cycle, because everything that follows hangs on it. Deep inside the sun, it's not solid, it's plasma, electrically charged gas, hot enough that atoms have been torn apart into a soup of charged particles. And when charged particles move, they make magnetic fields. The sun is, in a real sense, a gigantic, sloppy, churning magnet. But it doesn't spin like a solid ball. Its equator turns faster than its poles, so over time, the sun's magnetic field gets wound up, stretched, and tangled, like someone twisting a rubber band tighter and tighter and tighter. Those twisted, concentrated knots of magnetic field are what punch through the surface and become sunspots. More twisting, more knots, more spots. And the number of sunspots rises and falls on that 11-year rhythm. Scientists have been counting them, by hand and by telescope, for centuries. It's one of the longest continuous scientific records we have. When the count climbs to its high point, that's solar maximum. When it bottoms out, solar minimum. The cycle we're in, cycle 25, is the 25th cycle we've numbered since careful record-keeping began back in the 1700s. And here's the milestone that frames this entire story. In October of 2024, NOAA and NASA jointly announced that cycle 25 had reached its maximum. The smoothed sunspot number topped out right around then. And this past February, the trackers who watch this most closely noted that the sun appeared to have formally exited the solar max phase, past the summit, onto the downslope. Now picture a mountain. The peak looks like the dangerous place. Thin air, exposed, dramatic. That's where you'd expect the trouble. But ask any mountaineer where most accidents actually happen, and they'll tell you the same thing. The descent. Coming down. When you're tired, when your guard is down, when you think the hard part is behind you. The sun's descent works in a cruel, similar way. As the cycle winds down, the total number of sunspots drops. The face of the sun gets quieter, on average, fewer flares per week. The headlines fade. People stop paying attention. The grid operators, the satellite companies, the airlines, the public. Everyone exhales. And that exhale is the problem, because the declining phase of a solar cycle is not safe, not even close. Some of the most violent space weather we have ever recorded arrived after the peak, when the world had already stopped watching. The danger doesn't switch off when the sunspot count drops. It just gets quieter on average, and a lot less predictable. Let me put it as plainly as I can, because it's the whole spine of this video. The sun passing its maximum is not the same thing as the sun becoming safe. Those are two completely different claims, and we have spent decades quietly confusing them. Why would that be? It seems backwards. Fewer sunspots should mean less danger, not more. The full answer is what the next few minutes are about, but here's the seed of it. As the cycle declines, two things happen at once. The regions that do appear can still be enormous and violent, the magnetic spring just as tightly wound as ever, only now there are fewer of them competing for attention, and the sun opens up great wounds in its outer atmosphere, called coronal holes, that fling high-speed streams of solar wind at Earth over and over, like a sprinkler that won't shut off. Quiet on average, punctuated by individual events that can be the worst you'll ever see. A fading cycle isn't a disarmed one. It's a quieter room with the same loaded gun on the table. And on the solstice, that gun went off, just enough to remind everyone it's still there. So what exactly is the thing we're afraid of? What's the real disaster scenario? It's time to talk about the flash and the cloud. Everything we've covered so far, the flare, the R2 blackout, the radio dropping out, all of that comes from the flash, the burst of X-rays and light. It's fast, it's over in minutes, and as alarming as a blackout sounds, a radio blackout is a temporary inconvenience for most people. The flash is not what keeps space weather scientists up at night. What keeps them up at night is the cloud. Some flares, especially the big ones from those tightly wound regions, don't just emit radiation, they blow off a chunk of the sun's own atmosphere. Billions of tons of magnetized plasma hurled into space at speeds that can top 1,000 miles per second. That's a coronal mass ejection, a CME. And if one launches straight at us, it doesn't arrive in 8 minutes. It takes 1 to 3 days to cross the gap. Which, by the way, is the good news. The cloud is slow enough that we get a warning. NOAA's forecasters can watch it leave the sun, model its path, and tell us roughly when it'll hit and how hard. 1 to 3 days is enough time to act, if anyone's listening. Here's what happens when the cloud arrives. That mass of magnetized plasma slams into Earth's magnetic field and shakes it, hard. And a shaking magnetic field does something that turns a beautiful sky into an infrastructure problem. It induces electric currents. In anything long and conductive, in pipelines, in railway signals, and above all, in the high-voltage power lines that string across entire continents. These are called geomagnetically induced currents. Say it with me, because it's the phrase that matters most in this whole field. Geomagnetically induced currents. Direct current, leaking into a grid that was built to handle alternating current, sneaking in through the grounded necks of the giant transformers that step voltage up and down across the country. And a transformer fed a current it was never designed for doesn't just trip a breaker and reset. It overheats. It saturates. In the worst case, it cooks itself from the inside, permanently, in a way that can take months or longer to replace, because the biggest ones are custom built, and there is no shelf to pull a spare off of. Think about that for a second. We're used to blackouts that last hours. A bad storm, a downed line, the power's back by morning. This is a different category of problem. This is damage measured not in hours, but in seasons. A regional grid that doesn't come back for a year because the parts to fix it have to be built from scratch. That's the disaster, not the flare. The storm behind the flare, frying the machines that keep the lights on, during the phase of the cycle when everyone assumed the danger had passed. And we are not guessing about whether this can happen. We don't have to guess, because it has happened. More than once, in living memory, the sun reached down and touched the grid, and the storm that did it the first time caught a world that had no idea it was even possible. Let me take you back to that one. A March night in 1989 in the province of Quebec. It's just after midnight, Universal Time, on March 13th, 1989. 2 days earlier, the sun had launched a series of coronal mass ejections from a giant sunspot region. Those clouds are now arriving at Earth, one behind the other. At 27 minutes past 1 in the morning, the storm hits in earnest. Up in the sky, the auroras go berserk. People as far south as Texas and Florida look up and see red light rippling overhead, so vivid that some call emergency lines convinced something is on fire. In Canada, the lights are dancing over Quebec. And underneath those lights, in the high-voltage lines of the Hydro-Quebec power grid, something invisible is building. The shaking magnetic field is pushing induced currents into a network that snakes for hundreds of miles across rock that doesn't conduct electricity well, which, it turns out, makes the problem worse. The currents surge into the transformers. Protective systems start to sense that something is deeply wrong. Then it goes. In 90 seconds, the entire Hydro-Quebec grid collapses. 90 seconds. Let me put that in human terms. That's less time than it takes to read this paragraph out loud. In a minute and a half, 6 million people lose power. In the dark. In a Quebec March, where the overnight cold can kill. The outage lasts about 9 hours. Water treatment falters. The Montreal Metro stops. The airport goes dark. Estimates of the total cost run into the billions. And it nearly went further. Across the border, in the United States, transformers felt the same currents. One large transformer, at a New Jersey nuclear plant, took damage that would cost a fortune to repair. The same storm that blacked out Quebec was tugging at the American grid too. We were closer to a much larger disaster than most people ever realized. That is what a coronal mass ejection can do to a modern grid. Not in theory. It happened. And the storm that did it has a name among the engineers who study this. They call it the archetype, the benchmark, the one everything else gets measured against. Now here's where I have to be straight with you, because being straight with you is the entire point of this channel. You'll hear it said, a lot, that the great storms only strike on the way down from the peak, that the descent is the dangerous part, full stop. It's a clean story, and it's too clean. Quebec, in '89, did not hit on the quiet downslope. It hit close to the maximum of its cycle. The peak of that cycle came later the same year. So no, the worst storms are not politely confined to the declining phase, and I'm not going to pretend they are. But sit with the real lesson, because it's worse than the tidy version. The danger isn't parked at the peak and gone afterward. It's smeared across the entire back half of the cycle. Solar maximum is a label on a chart. The sun doesn't read the chart. A loaded region can fire 2 years after the official peak just as easily as 2 months before it. That's not a comforting thought. A tidy rule you could plan around would be comforting. This isn't that. This is a long, uneven stretch of years where the threat never fully switches off. It only fades and flares, fades and flares. And the single best proof of that came 14 years after Quebec, in the autumn of 2003, when the sun was supposedly winding down for good. We'll get there. But first, you need to see the event that makes even Quebec look small. For that, we go back another 130 years, to a clear September morning in 1859, and a young astronomer sketching sunspots through a brass telescope. September 1st, 1859. A British astronomer named Richard Carrington is in his private observatory, doing what he does most clear mornings, projecting an image of the sun onto a screen and carefully sketching the sunspots. On this morning, there's a huge, complex group of them. And then, right in front of his eyes, 2 brilliant points of white light erupt over the sunspots. So bright, they outshine the projected surface of the sun itself. Carrington thinks at first that a beam of unfiltered sunlight has broken through. It hasn't. He's watching, live, the first solar flare ever recorded by a human being. A white light flare, which means it was a monster. What he can't see is what came with it. a coronal mass ejection, aimed almost straight at Earth, moving so fast it crossed the gap in well under a day instead of the usual 2 or 3. When it arrived, the sky came apart. Auroras erupted over almost the entire planet, not just the poles. People saw them in Cuba, in Hawaii, in Colombia, near the equator, where no one alive had ever seen such a thing. In the northeastern United States, the glow was so bright that people woke in the middle of the night thinking it was dawn. Gold miners in the Rockies got up and started cooking breakfast at 1 in the morning, fooled by the color. And then the technology of the day began to fail. In 1859, the cutting edge was the telegraph, the world's first electric nervous system, copper wires strung between cities. The storm induced currents in those wires, just like it would in a power grid a century later. Telegraph operators got electric shocks, paper tape caught fire, sparks jumped from the equipment. And here's the detail that should give you chills. Some operators disconnected their batteries entirely and found the line still carried enough current, straight out of the charged sky, to keep sending messages. The Earth itself had become the battery. Think about that for a second. The wires didn't need their power source anymore. The storm was powering them. Now imagine that storm hitting today. We don't have a few telegraph wires. We have a planet wrapped in conductive infrastructure, continental power grids, hundreds of satellites your daily life quietly depends on, for navigation, for timing, for the financial transactions that clear in milliseconds, undersea cables, pipelines. A Carrington-class event in 2026 wouldn't shock a telegraph operator. It could knock out the giant transformers at the heart of the grid across whole regions at once, the ones that take a year or more to replace. And there aren't many spares. Studies that try to put a number on it land in the trillions of dollars, with recovery measured not in days but in months or years. That's the high end, the genuinely bad day. And like Quebec, the Carrington event struck close to the maximum of its own solar cycle, not on the descent. So if both of the legendary storms hit near their peaks, why am I telling you that the years after the peak, the years we just entered, still matter? Because of what happened in 2003. And 2003 is the one that should change how you hear the phrase, "the sun is calming down." By the autumn of 2003, solar cycle 23 was old news. Its peak had come and gone around the turn of the millennium, roughly 3 years earlier. The sun was, by every reasonable expectation, on its long slide toward minimum. The exciting years were over, or so the calendar said. Then, in late October, a sunspot region rotated into view that the sun apparently hadn't gotten the memo about. It was catalogued as active region 10486, one of the largest of the entire cycle, more than a dozen times the width of the Earth, and its magnetic classification was Beta Gamma Delta. That phrase again, the same coiled spring label sitting on the region that fired the Solstice flare this weekend. Hold that thought. What followed is remembered as the Halloween storms. Over about 2 weeks, that region and its neighbors fired off 17 major flares. 17, including, on November 4th, the single most powerful flare ever recorded by our satellites. It was so intense it saturated the detectors, pinned the needle, and had to be reconstructed afterward. The estimate landed around X28, possibly far higher. For comparison, the Solstice flare this weekend was an M7. The Halloween monster was in a different universe. The CMEs came in waves, some moving at well over 1,000 miles per second, and they hammered Earth's magnetic field into a G5, top of the scale, the most severe category there is. Here's what that did. In southern Sweden, in the city of Malmö, about 50,000 people lost power as a transformer was pushed past its limits, its oil heating up from the induced currents. Down in South Africa, a country at low magnetic latitude, where this isn't even supposed to be a serious risk, around a dozen transformers were damaged badly enough that they had to be replaced. Airliners were rerouted off the polar paths to dodge the radiation and the radio blackouts. GPS signals degraded. Satellites went into safe mode, some were damaged, and a sun-watching spacecraft briefly went dark. Auroras were seen as far south as Texas, Florida, and the Mediterranean. And all of it, every bit of it, happened about 3 years after that cycle was supposed to have peaked. On the downslope, in the declining phase that scientists in their own papers describe in plain language as exactly when these energetic events keep hitting Earth. That's the lesson. Not that the danger waits for the descent, that the danger doesn't end with the peak. Maximum passing isn't the all clear, it's halftime. So now, bring it home to right now. To this week, Cycle 25 passed its maximum back in the fall of 2024. This past winter, the trackers marked the sun as having left the solar max phase. We are, today, standing in the early part of the exact same kind of descent that produced the Halloween storms. And on the solstice, a fresh beta-gamma-delta region, the same dangerous magnetic recipe as the 2003 monster, announced itself with an almost X-class flare. I'm not telling you a storm is coming this week. In a moment I'll show you exactly how quiet it actually is right now, because honesty cuts both ways. But I am telling you that the calendar on the wall, the one that says the sun is settling down, is the most dangerous thing in the room, because it makes us look away, and there's something out there, right now, that we should not be looking away from. It's on the far side of the sun, and it's growing. For most of the time, we can only see one side of the sun, the side facing us. The far side is a blind spot, except for a few spacecraft parked at angles that let them peek around the edge. One of those spacecraft is Europe's solar orbiter, and a couple of days ago, on June 20th, it sent back an image of the sun's far side that got people's attention. There's a sunspot region back there, and in the span of just a few days, from around the 16th to the 20th of June, it didn't just grow, it multiplied in size more than tenfold. A small mark became a sprawling complex, fast. Here's why that matters. The sun rotates, roughly once every 27 days as seen from Earth, which means that region on the far side is not going to stay on the far side. It's turning toward us. In the coming days, it rotates onto the Earth-facing disk, and we get our first direct look at just how big and how organized its magnetic field really is. It might fizzle. Regions do that. They look fearsome on approach and arrive as duds, their magnetic fields simpler and calmer than they seemed. That happens all the time, and it would be the boring, likely, perfectly normal outcome. Or it rotates into view still tightly wound, joins the already active region 4473, crossing the disk right now, and the sun has two loaded regions pointed our way at once, on the descent, with months of summer hurricane season ahead. NOAA's forecasters, looking at 4473 alone, have already nudged up the odds of more flares over the next few days. So that's the watch item. Now let me keep my promise and give you the honest other half. Right now, as I record this, it is calm out there. Genuinely calm. The planetary K-index, the number that tracks how disturbed Earth's magnetic field is, on a scale from 0 to 9, is sitting near 1. Near the bottom, there's no geomagnetic storm in progress, and none in the official forecast for the next couple of days above the mildest level. The two clouds that did launch from the sun around the 19th and 20th of June are expected, at most, to deliver a glancing blow, the kind that might lift the needle to a minor level and nothing more. And if you were hoping I was about to tell you to run outside tonight and catch the aurora across the lower 48, I'm not. The geometry isn't there this week, and even if it were, we're at the solstice, the shortest nights of the year. In much of the country the sky barely gets dark enough. This is the part the fear channels skip, the boring, true part. The sun fired a notable flare, there's an interesting region rotating in, and at this exact moment the space weather is quiet. All of those things are true at once. That's not a contradiction. That's what an honest forecast looks like. But quiet is not the same as safe. And to see why a quiet sky over your head can still be sitting on top of a fragile system, we have to come down out of space and look at the machine an event like this would actually break. Your grid, your sky, your country specifically. So let's talk about the machine. The North American power grid is one of the largest, most complex things humans have ever built. Thousands of power plants, hundreds of thousands of miles of high-voltage transmission line, all synchronized, all humming at the same frequency, all depending on a relatively small number of very large, very expensive transformers to move that power across the country. And here's the uncomfortable truth about those big transformers. They are not something you buy off a shelf. The largest ones are custom-built, often overseas, weigh hundreds of tons, and can take a year or more to manufacture and deliver. We don't keep a deep bench of spares, so if a geomagnetic storm cooked a batch of them at once, you couldn't just swap them out over a weekend. The repair timeline is the disaster, not the storm. The wait. Picture your own town after a hurricane or an ice storm. The power's out, but crews are already rolling, and you know, in your bones, that it's coming back. Maybe days. That knowledge is what keeps people calm. Now take that knowledge away. Tell a whole region that the parts to fix the grid are being built from scratch on another continent and won't arrive for the better part of a year. That's not a longer version of a normal blackout. That's a different kind of event entirely, and we've never lived through one at scale. Geography matters here too, and this is where it gets personal, depending on where you're watching from. The risk isn't even across the country. Geomagnetically induced currents are worst at higher magnetic latitudes, and worst over certain kinds of rock, the ancient, hard, electrically resistant bedrock that forces the currents up into the grid, instead of letting them drain harmlessly through the ground. That combination puts a bullseye on the northern tier of the United States. The upper Midwest, Minnesota, Wisconsin, Michigan, the northern plains, New England up into Maine. If you live across that band, you live on the part of the grid most exposed to a bad day on the sun. Now, the good news, and there is some. We are not asleep at the wheel the way we were in 1989. After Quebec, the people who run the grid started taking this seriously. Today, there's a federal reliability standard, known by the label TPL 007, that actually requires utilities to study how a severe geomagnetic storm would hit their systems, and to plan for it. Operators can take protective action when a big storm is forecast, reduce load, postpone maintenance that takes equipment offline, reconfigure the network to spread the strain. A storm we can see coming, 1 to 3 days out, is a storm we can brace for. That warning window is everything. But the grid is only the headline. The same space weather reaches into your life through a dozen quieter doors. Start with GPS. It's not just the little blue dot on your phone. The global positioning system is precision timing and precision location woven invisibly through modern life. And right now, across the middle of the country, it's the growing season. Modern American farming runs on GPS-guided tractors, steering themselves down rows to the inch, across Iowa, Illinois, Nebraska. A strong solar event scrambles the upper atmosphere those signals pass through, and that precision degrades. The financial system leans on that same satellite timing to stamp transactions in the right order. Then there's aviation. It's hurricane season. Flights get rerouted around space weather events the same way they get rerouted around thunderstorms, especially over the poles and oceans, where a radio blackout means a plane and the ground simply can't talk. And the satellites overhead, the ones carrying internet to rural areas, the low-orbit constellations, your television, your weather data, all of them live in an environment a solar storm turns hostile. A storm earlier in this very cycle knocked dozens of newly launched satellites out of the sky before they ever reached a stable orbit, because the storm puffed up the atmosphere and dragged them down. And the people who feel the radio blackouts first, the ones from that solstice flare, are some of the people we count on most. The Coast Guard, search and rescue, mariners offshore, ham operators who, when the cell towers and the internet go down in a disaster, are sometimes the only ones left who can get a message out. Which brings us to the scenario that actually worries planners. Not space weather alone, space weather landing on top of something else. Because a society can absorb one disaster at a time, it's when two arrive together that the cracks turn into canyons. Here's the scenario that keeps emergency planners honest. It's not the headline-grabbing Carrington repeat out of a clear blue sky. It's the ordinary disaster that gets a partner. Picture a major hurricane bearing down on the Gulf Coast. Category 4. The cone has been narrowing for days. Millions of people are being told to evacuate. Emergency managers are leaning on every communication channel they have. And a big slice of emergency communication, when the cell network is jammed or down, falls back on high-frequency radio. The same high-frequency radio a solar flare wipes out on the daylight side of the Earth in minutes. Now drop a solar flare into that exact moment, an R3, an R4, right during the landfall. The backup comms degrade right when they matter most. The GPS the rescue helicopters and the supply convoys rely on gets noisy right when every minute counts. Nothing about the sun caused the hurricane. The two events have nothing to do with each other. That's the whole point. They don't have to be related to happen at the same time, and when they do, each one makes the other worse. Or take a different version. It's August. A heat dome has settled over Texas. The grid, run by ERCOT, is already straining. Every air conditioner in the state pulling at once. Reserves thin, operators sweating every megawatt. The system is running hot and close to its limits with no margin to spare. That is the worst possible moment for a geomagnetic storm to start pushing induced currents into transformers already thermally stressed from carrying a record load. A grid with no slack, meeting a force that needs slack to survive. Heat from below, heat from above, meeting in the iron core of a transformer that was never built for either one alone, let alone both. And here's the cruel arithmetic of it. On a normal day, a moderate geomagnetic storm is a non-event for the Texas grid. Plenty of margin, plenty of slack, the system shrugs it off. It's only dangerous in the one window where the grid has already spent all its slack just staying alive through the heat. Same storm, completely different outcome. The sun didn't get any stronger. We just happened to be standing in the wrong place at the wrong time. I want to be careful here, because this is exactly the kind of talk that tips over into doom-mongering, and that's not what we do. These compound scenarios are not predictions. I am not telling you a flare is going to take down the grid during the next hurricane. The odds of any single severe storm hitting that one perfect, terrible window are low. The grid is more resilient than it was in '89. Operators have playbooks now. And in the everyday case, the most likely thing a region like 4473 does over the next 2 weeks is rotate across the face of the sun, fire off a few more flares that cause a few more hours of radio static somewhere on the daylight side, and then rotate out of view, having changed nothing about your life. That's the base case. That's what usually happens. I'd be lying if I dressed it up as anything more. But low odds are not no odds, and the thing about a system with no margin is that it doesn't fail gracefully. It fails all at once. The reason planners run these scenarios isn't to scare you. It's the opposite. It's so the warning window actually gets used. So that when NOAA flags a serious storm 1 to 3 days out, the grid operators and the airlines and the emergency managers act on it, instead of waiting to see. Which raises the obvious question, how do they see it coming at all? How do you forecast the weather of a star 93 million miles away? Because if that warning window is the thing that saves us, you should know exactly how it works, and exactly how much and how little it can really tell us. Forecasting space weather is younger and harder than forecasting the weather outside your window, but the basic idea is the same. You watch the source, you track what it throws, and you measure what's incoming before it arrives. It starts with watching the sun itself, constantly. A fleet of spacecraft and ground telescopes stares at it around the clock. A pair of satellites called GOES, the same family that watches hurricanes from orbit, carries instruments that measure the sun's X-ray output second by second. When a flare goes off, it shows up as a spike on that X-ray plot almost instantly, and the height of the spike is what gives the flare its letter and number. That M7 on the Solstice? That's a value read straight off the GOES X-ray monitor. That's where these classifications come from. Not a guess, a measurement. But a flare, remember, is the flash. It arrives at the speed of light, so seeing it is the same instant as being hit by it. There's no lead time on the flash. The forecasting that actually buys us time is about the cloud, the CME. When a coronal mass ejection blows off the sun, instruments that block out the sun's blinding disk can photograph the cloud itself, expanding outward into space. From those images, forecasters estimate its speed, its direction, and roughly how much of it is aimed our way. Then they feed that into computer models. The main one NOAA uses goes by the name Enlil, after an old storm god, and it simulates the cloud barreling through the solar wind to predict when its leading edge reaches Earth. That's where the 1 to 3 day warning comes from. The model gives you an arrival time and a rough severity. Think of it like tracking a hurricane that crosses an entire ocean in 2 days instead of 2 weeks. Same logic, much less time, and a cone of uncertainty that's just as real. And then, for the final confirmation, we have a tripwire. About 1 million miles upstream of Earth, toward the Sun, sits a small set of spacecraft parked at a special gravitational balance point. As the cloud sweeps past them on its way in, they measure it directly. Its speed, its density, and the single most important thing of all, the direction of its magnetic field. Because here's the quirk that decides everything. If the cloud's magnetic field points the same way as Earth's, it mostly slides around us, and the storm is a dud. If it points the opposite way, it links up with our field and pours its energy straight in, and the storm is severe. And you often can't know that for certain until the cloud crosses that tripwire, which gives us our most reliable warning, and it's only about 15 to 60 minutes. Let me say that plainly, because it's humbling. Our best, most certain heads up that a severe storm is actually about to hit can be less than an hour. Enough time to put a grid into a protective posture if everyone's ready and watching. Not enough time to build a single transformer. That's the honest state of the art. We've gotten dramatically better at this. NOAA's Space Weather Prediction Center issues watches and warnings the same way the National Weather Service does for tornadoes, and grid operators and airlines really do act on them. But we cannot tell you a week out that next Tuesday is the day. The sun doesn't work like that. We can tell you which regions are loaded. We can tell you when a cloud is on its way. We can give you that final tripwire confirmation in the last hour. That's the system. It's good. It's not magic. So when you hear someone announce, with total confidence, that a catastrophic solar storm will strike on a specific date weeks from now, you can stop listening right there. Not because the catastrophe is impossible, because that's not how any of this works, and the certainty is the tell. Which brings us to the part of this video I think matters most. The part where we separate what the sun can actually do from the things people have decided to believe about it. If you spend any time at all searching for solar storms online, you'll run straight into a wall of fear that has very little to do with the science. So let's clear it, one claim at a time, because the truth is strange enough without the inventions. Claim 1. We're heading into a grand solar minimum, a mini ice age. The sun is shutting down. You'll see this one everywhere. Here's the problem. Cycle 25, the one we're in, came in stronger than the official forecasts predicted. It overperformed. A cycle that just ran hotter than expected and is only now easing off its peak is not a sun that's switching off. Even in the real historical cold spell people point to, centuries ago, the link to climate was small and regional, nothing like the global deep freeze the videos promise. The sun is doing something completely ordinary. It's coming down off a peak, the way it has done dozens of times in the records we have. Claim 2, and this is the big one in this whole field. Solar flares cause earthquakes. The sun acted up, and 3 days later there was a big quake somewhere, so one caused the other. It's a powerful story, because our brains are pattern-matching machines. But it doesn't survive contact with the data. Researchers have gone looking, carefully, through long catalogues of flares and quakes, and found no meaningful connection. And the physics tells you why. A solar storm pushes electrical currents through long conductors near the surface. It does not reach miles down into the crust and pry apart a locked fault, holding back the stress of continental plates. The energy isn't there, in the right place, in the right form. There are big earthquakes constantly. There are solar events constantly. Line up any 2 streams of common events and you'll always find pairs that look spooky. That's coincidence wearing a costume. Claim 3. The micronova. The idea that the sun periodically detonates and scorches the Earth on a schedule, and we're somehow due. This one comes from a specific corner of the internet, and it is not a thing. Our sun is not the kind of star that does that. There's no evidence, in the ice, in the rock, in the tree rings, of the sun ever having flash-fried the planet. It's science fiction with a channel. And claim 4. The gentlest one, but the one that erodes trust the fastest. The breathless aurora alerts. Step outside tonight. The whole country will see the northern lights. Most nights that's flatly wrong, and tonight it's wrong twice over, because the field is quiet and it's the solstice. When the aurora really is coming for the lower 48, NOAA says so plainly, and so will anyone honest. The constant false alarms don't make anybody safer. They make people stop listening. And the day it actually matters, that's the worst possible thing. Now, where is there real scientific debate? Because honesty runs in both directions. There's genuine, open argument about exactly how often a true Carrington-scale event happens, about how badly a worst-case storm would really hit a modern grid, since, thankfully, we've never taken a direct Carrington-level shot in the age of continental power, about how much warning we can realistically squeeze out of the system. Those are live questions, argued by serious people, and anyone who tells you they're settled is overselling. Here's what I want to leave you with on this. Strip away the chemtrails, the secret weapons, the doomsday clocks, all the stories that quietly comfort us by insisting that somebody, somewhere, is in control of the sky. The reality underneath is more unsettling than any of them. There's no schedule, there's no hidden hand, just an ordinary star, behaving exactly as stars do, 93 million miles away, occasionally flexing in a way our wired-up civilization happens to be exquisitely sensitive to. No one is steering it, no one is targeting us, and no one can switch it off. The truth is scarier than the conspiracy, because the conspiracy at least has someone in charge. So if no one's in control, and the warning window is short, the obvious question is the practical one. Is there anything you, personally, should actually do about any of this? There is, and it's calmer than you'd think. So, practically, what do you actually do with all of this? And I want to be careful, because the answer the fear channels give you, the bunker, the gold, the panic, is both useless and a little insulting. Here's the calm version. First, and this costs you nothing, you can simply watch the same thing the professionals watch. NOAA's Space Weather Prediction Center puts its forecasts out in the open, for free, in plain language. The 3-day forecast, the active watches and warnings, the current state of that K-index number we keep coming back to. There are good apps and dashboards that pull the same official data and will ping your phone when a real geomagnetic storm is on the way. Not a rumor, the actual government forecast. And if you've ever wanted to catch a genuine aurora, that's also how you do it. You wait for NOAA to say a real storm is incoming, and you ignore everyone who says it sooner. Second, the boring household stuff that's worth doing anyway. The single most useful preparation for a long power outage of any cause, a hurricane, an ice storm, a wildfire, a once-in-a-century solar event, is exactly the same. A little water, a little food that doesn't need refrigeration, a way to charge a phone, a battery radio, a flashlight that isn't your phone. None of that is solar storm prepping. It's just being a person who's ready for the lights to go out for a while, which is going to happen to most of us at some point, regardless of what the sun does. The sun is just one more reason to do the thing you already should. And notice what that means. The smartest preparation for the scariest space weather scenario is identical to the preparation for the most ordinary bad weekend. There's something almost reassuring in that. You don't need a separate plan for the sun. You need the plan you should already have. Third, and this is the one that actually moves the needle, it's not on you at all. It's on the grid. The real protection against a Carrington-class event isn't in your garage. It's in hardening the transformers, building spares, and giving operators the authority and the playbook to act fast on a warning. That's policy. That's the utilities and the regulators, and the standard we talked about, TPL 007. The most powerful thing an ordinary person can do is understand the problem well enough to support taking it seriously, instead of rolling their eyes because the only voices they've ever heard on it were screaming about the apocalypse. That's really the whole point of this channel, if I'm honest. The screaming doesn't protect anyone, it just burns people out until they tune the whole subject out, and a tuned-out public is exactly what you don't want when a real warning finally comes. Calm, informed attention is the actual goal, not fear. Attention. And the people who give you the real signal are worth knowing by name: the Space Weather Prediction Center, the space weather scientists who post the honest, measured forecasts, the ones who'll tell you when it's nothing, which is most days, so that you'll believe them on the rare day it's something. Those are the voices to follow, the ones willing to bore you. Boring, from a space weather forecaster, is a feature. It means they're not selling you anything. And if a forecaster ever hands you a specific catastrophic date, weeks out, with total confidence, you've found the exception. Walk the other way. The honest ones deal in probabilities and windows, never in certainties, because the sun has never once handed anybody a certainty. So here's where we've landed. A region called 4473 threw an almost X-class flare on the solstice. It knocked out some radio for an hour on the daylight side of the planet, and that was the whole immediate story. The sky tonight is quiet. The K-index is near the floor. There's no storm bearing down on your town this week. And yet none of that is the reason this mattered enough to spend the last hour on. Let me take you back to the question I planted at the very beginning. I said the dangerous part of this flare wasn't the flare, it was when it happened. It's time to actually answer that. So why did the timing matter? Because we're standing at the one point in the solar cycle where human attention naturally falls away. The peak is behind us. The headlines have moved on. The phrase "the sun is calming down" is doing its quiet work in the back of everyone's mind, telling us the show's over, telling us to look somewhere else. And the history we walk through tonight says that's precisely backwards. The most destructive geomagnetic storms aren't politely confined to the loud years at the peak. Quebec hit near a maximum. Carrington hit near a maximum. But the Halloween storms, the strongest flare ever recorded, the G5 that reached into Sweden and South Africa and rerouted flights over the poles, that came 3 years into the descent, when the world had already decided the danger was over. The peak being behind us is not the all clear. It's the part of the climb where people get hurt. Say it to yourself one more time, because it's the one thing from this whole video worth keeping. Maximum passing is not the all clear. It's halftime. That's the answer. The solstice flare matters not because it was big, it wasn't especially, but because of the chapter of the story it arrived in. A fresh, tightly wound region, the same magnetic recipe as the 2003 monster, raising its hand on the longest day of the year, at the exact moment we'd all agreed to stop paying attention. So here's where I'll leave you, and I'm not going to tie it in a bow because the sun doesn't. Region 4473 is still crossing the disk right now, loaded, with most of its journey across the face of the sun still ahead of it, and behind it, on the far side, that other region, the one that grew more than tenfold in a few days, is turning slowly toward us. In the coming days, it rotates into view. Maybe it's nothing. Maybe it arrives a dud, its field gone calm, and we never speak of it again. That's the likely outcome, and I hope it's the one we get. Or maybe it doesn't. Maybe it comes around the edge still wound tight, and for a stretch this summer, the sun has 2 angry regions pointed our way at once during the descent, with hurricane season open beneath them. We won't know until it turns to face us. Nobody will. Not me, not the fear channels, not NOAA. We'll all find out together in a few days when the sun decides to show us. And that, in the end, is the part the conspiracies can't stand, and the part I find strangely calming. We are not in a story with a villain and a schedule. We're in a story with a star, and a blind spot, and a few days of waiting. No one knows what's behind the edge yet. That's not a cover-up. That's just the honest shape of the unknown. I'll be watching the real numbers when it turns. The honest ones. And if it becomes something, you'll get the calm, sourced version here, with the data on the screen, the same way we did tonight. Here's what I'd watch next, though, while the sun takes its time, because there's another corner of this planet that has been quietly refusing to settle down, and it has nothing to do with the sky. A year ago, one of the largest earthquakes ever recorded tore open the seafloor off the coast of Kamchatka and sent waves racing toward Hawaii. It triggered tsunami alerts from Japan to the coast of California, and just days ago that same stretch of fault started moving again. The question nobody's answering is whether the sequence that produced the monster is actually finished or just resting. That's the story I'd watch next. I'll see you there. This has been the Horizon Lab. Stay curious, keep looking up, and keep your feet on the ground.